Okay, so we'll invent a few logic expressions. So we'll say something like AD, which is the input to the D flip-flop for variable A, is equal to, let's have three different variables. So C, B, not C, BA, plus, I don't know, B not A, for example. We can do another one. Let's call that B. Okay, something like that. So what we then need to do is have some flip-flops that will be driven by all of this. We should actually have a C flip-flop as well. We'll make that one easier. We'll just say it's not C.
Wait, has it started already?
1:30?
Yeah.
Yep. So it's 37 past 1 now. Yeah, so it's a shoot. So we're just going through some questions and things from the assignment.
Ah, cool.
Okay. Daylight savings, tricked you. A few weeks later. Okay, so let's start drawing this. Easiest way to draw it is first draw our flip-flops. So we've got three flip-flops. So what comes out of them is the A, the B, and the C. What goes into them is the CD, BD, AD, like that. Then we need to draw this expression, or each of these expressions, leading into here. Okay, so what have we got? We've got an inverter, we've got a 2-input AND gate, and we've got a 4-input OR gate. We can just draw our inverter is the easiest one. Okay, so C is equal to not C, so we invert the signal. We then have let's do this expression here. So we have an OR gate there. Sorry, an OR gate, the other one. And then feeding into that OR gate, we have two AND gates. Now those AND gates are all 4 inputs. So they're 2 inputs. So we'll need some extra ones in that case. Oh no, this one's fine. 2 inputs, 2 inputs. Our OR gates are 4 input. So in that case, if we've got 4 inputs, we can't just leave the other 2 floating. We need to do something with them. So we'll tie them to ground. Okay. If we're doing it with AND gates, we'd need to tie them to a high voltage so that we could actually get an AND output. With OR gates, we need to tie any unused ones to ground because we're not using them. Okay. Then we have, what have we got? Generally out of these, we'll also have a not C signal, a not B signal, and a not A signal as well, because it gives us D flip-flops give us a Q and a Q bar output. So this one here, we could have actually gone straight from here. That's the other way to do it. So what we can then do is we're doing this one. We can say that's C, not B, and that's A, B. And so those signals, we could draw them in physically. This one, I'll do it in a different color so it's more obvious. This one traces all the way back to there. This one traces all the way back to there. It starts getting a bit messy. So I'm happy with labels to specify. The labels are much easier to read anyway. Now, the only other thing is, this statement here is a little bit trickier. How do we produce a 3-input statement with only 2? And essentially, the way we do it is like this. So, not C, B, and A. And the output there will be like that. Okay? Then obviously we'll have our other one. That will feed into an OR gate, and that will feed into here. And so this would be BA. The final thing that you need to do for each of them is look up the data sheets. I don't have the data sheet on me, but the data sheet will show you each of the devices. So it will have a device like this and say, this one's, for example, VCC, this one's ground, and it will show you all the pinouts of how everything's connected together. So it might be 2, 3, 2, 3, and 4 or something like that. And you need to start labeling this. So that might be 2, 3, 4, and you label them on the schematic. It just makes it easier if you actually had to physically build this circuit, that you could just look up the data sheet, or you've got the data sheet there, you just plug the wires in those particular slots, and makes it very easy to debug as well. Okay, does that clarify things?